I'm Alan, and I'm a year 3 physics student. And like, not like them, I didn't do anything new or exciting. I just, yeah, I was just learning something and did some experiment using quantum computer. And so in this presentation, I will just briefly introduce what quantum computing is and how to use it to test quantum entanglement is non-local. I will introduce the quantum bits first, and then I will show how to entangle a pair of qubits, and at last I will show I will explain what Bell test is and how it counters classical mechanics. First of all, I bet you've already known what classical bit is. It's in any classical computers, you have a lot of bits. It's either 0 or 1, but in a quantum computer, we have qubits. And I will explain qubit. This is called block sphere. So basically it means we are using spins in a quantum computer, and the qubit is like a spin. It can point to any direction on this sphere, but it's not a classical object. So if you measure it in this direction, then it won't be in a particular position. It will just collapse into either spin up or spin down. So if you measure it, it's still 0 or 1. It's just when you didn't measure it, it's in a superposition. So it's like this. And so these are some classical gates. For example, this one is like a NOT. It's flipped the 0 to 1 and 1 to 0. And this is a condition gate. So it means X is target and Y will flip on the condition of X. And similarly, we have some quantum gates in quantum computers, but some local rotations, because even for one single qubit, you can do many different operations to it. So it's not just that NOT. And C naught is basically a similar idea to that classical one. And this is just how IBM platform look like online. And basically, you can build some quantum circuit here, and this is a simulator. But it won't work if you have many qubits, and then you click set up and run. Now I will show you how to entangle a qubit on that IBM. First, you use this Hadamard. It basically flip this first qubit to a superposition between up and down, and then you use a C naught, so that now these two qubit will be either both spin up or spin down. You can set up and run. This means measurement, and this is a real experimental outcome of that circuit. And here you can see that it's indeed entangled, but with some arrows. I don't know if you have wondered that maybe quantum entanglement is not quantum. Maybe it's classical, with something hidden inside and making it probabilistic. So this Bell test basically give you a experimental method to verify whether the quantum entanglement is really quantum. So the basic idea is we have Alice and Bob, and I secretly tell Alice to write down maybe a number on A, and then for Bob, I tell him to write a number maybe on B prime. And then I separate them far away that they cannot communicate. And Alice doesn't know what Bob is on which side of board he's writing. And then I let them write down a number, either 1 or -1. Then I collect the two numbers they write and multiply them together. So it would be 1 or -1. And then if they're writing, if I told them to write AB, I take down that number, multiply that number here. And if it's A, B prime, I take down here. So I'll just record all numbers and repeat the experiment for a lot of times. Then I get the average value of each numbers. I add the first 3 and minus the fourth one. Then by this setup, you can see that classically, the best strategy for the E to reach its maximum is just everyone write 1 on either one side of the board. So then the maximum of E will be 2. But in quantum mechanics, it can be different, because before Alice and Bob are separated, we can prepare them with a pair of entangled qubits I just prepared. And now if Alice was told to write a number to A, then she measures the qubit in this direction. And if she was told to is told to write down A prime, then she measured this direction. And the idea is that when the number is AB, then the angle of these two measurement direction is 45 degrees. So the average of AB will be cosine 45 degrees. It's 1 over square root 2. And similarly, AB prime's angle is also 45 degrees, and this 1 over square root 2. And similar for A prime B. But for A prime B prime, the angle is 135 degrees. So it's negative 1 over square root 2. But then E's definition is these three add up minus this one. So theoretically, the expectation will be about 2.8. So it should exceed the classical range. Well, to prove this, you need some linear algebra. So I just skip it here. And this is how you use it, how you just use that setup in a quantum computer. And these are the measurement results. There are some errors indeed, but when you do the calculation, you'll find out that in this experiment, E equals to 2.6. It doesn't reach that 2 root 2, but it's still significantly outrange the classical region. Now I'll explain the reason behind this seemingly paradox between classical mechanics and quantum mechanics. The core idea is that classically, when we think of two people far away, we think their decisions are completely uncorrelated, which means the average of this AB at one time should equals to they completely have no idea what the other are doing. So AB's average should be equals to A's average times B's average. And using this equation, we can just change everything into this. And then A's average is just between minus and 1. And every other, and B, you can just plug in numbers and you can see the maximum should only be 2. But quantum mechanically, this isn't true. And this actually means local realism. But so just quantum mechanically, you can imagine that once two objects are entangled, they are not they're not two separate things anymore. No matter how far away they were separated, they are still in one statistical system. And that's why they are correlated. But nevertheless, the causality and the realism isn't against. Yeah, so that's the reasoning behind. Thank you. And if you want to play with that quantum computer, you can just Google IBM Quantum.
Do they play with it?
Yeah, sorry?
They let you play with a computer remotely?
Yeah, IBM. But my experience is that although they said the most advanced quantum computer has about 1,000 qubits, I test that. Once the qubits exceeds maybe 10, then the entanglement ability is really poor. But just any real task in real life will need maybe 1,000 qubits. So I think there is still a long way to go. Yeah, I hope you enjoy it. Thank you.